Hi everyone, my name is Srija and I'm presenting our work on proving the safety of highly available distributed objects. This is a joint work with Gustavo Petri and Mark Shapiro. First, let's consider a centralized web application that serves users across several geographical regions. All users from all locations are connected to a single replica, and thus the perceived latency for the distant user would be very high. In order to lower the latency, the centralized object is distributed into three replicas across different continents, and the users are connected to the nearest replica. This ensures that we provide low latency service to the users. But this situation gives rise to concurrency bugs. I will show you an example how concurrency can violate an invariant. Let us examine an example of a distributed auction. Assume we have three different replicas distributed across the globe, and different users are connected to different replicas. So we have three users, Srija, Gustavo, and Mark, who are connected to three different replicas at Asia, Europe, and South America. A user, Srija, that's me, who is connected to a replica in Asia, has a painting to put up for an auction. The green dot near the painting indicates that the auction is open to receive bids. So Srija opens the auction, and this state is propagated to both Mark and Gustavo, who are connected to the European and American replicas respectively. Both of them are interested in the painting, and Mark placed the first bid for 100 euros. This update is propagated to Srija and Gustavo. Gustavo sees Mark's bid and places a higher bid for 105 euros. Unfortunately, at the same time, the connection between the replicas in Asia and South America broke down. Gustavo was able to propagate his update to Mark, but not Srija. Meanwhile, Srija is happy with Mark's bid, which is the only one she is aware of. She closes the auction, declaring Mark's 100 euro bid as the winner. When this is also propagated to Mark, he observes that despite placing the lower bid, he won. This is a violation of the invariant of a distributed auction that requires the highest bid to win. In the rest of the talk, I will show how to formally either prove the invariant is satisfied or point to a specific concurrent execution that violates it. In the later case, I will show how to fix it. Now let us look into the trade-offs for distributed objects. The ideal world for distributed objects would be having high availability and strong consistency. This eases reasoning about safety because the user has only to think about a sequential model of execution. But CAP theorem has proven that this is in fact a dream world. That is, distributed objects can either have high availability or strong consistency, not both. So where should we compromise? We have to maintain high availability because the whole point of distributing the service was to provide users a low latency, with low latency. So if the service is not available, it won't work. The next option we have is compromising on strong consistency and opting for eventual consistency. Eventual consistency is a very relaxed model of consistency, where it is assured that once all updates are eventually propagated to all replicas, all of them will be in the same state. We just observed in the previous example how this would violate safety of the object. So what should we do? In our real world, we have to provide high availability while being safe. For this, we present a proof rule to verify the safety of highly available distributed objects. Our proof rule is modular. I will explain how the specificity of propagating the states between replicas help us replace the more complex relay guarantee style of reasoning without the need to consider interleavings. We have implemented a tool that automates our proof rule that verifies whether a given specification is safe, and if not, provide counterexamples that helps the user get insight into the issues. Now, let us examine our proof rule using the auction example we discussed. Let us take a closer look into the auction example we discussed and observe how the state evolves. Initially, all replicas are in the same state without any active auction. When Srija starts an auction, the status of the auction changes to open, indicated by the green circle. This updated state is propagated to both Mark and Gustavo, and they merge the incoming state to their respective local states. So they have the auction status as open. Now Mark places a bid of 100 euros, and the state is propagated to Srija and Gustavo, who then merge this to their respective local states. Gustavo places a higher bid of 105 euro, which is propagated to Mark, and concurrently Srija closes the auction, declaring Mark as the winner. Mark receives the updated state from Srija as well, merges them into his own state, and observes that the state is unsafe because the bid with the lower amount wins. To address this problem, we first need to define safety. Basically, we must identify the invariants of an object. For our auction example, the object-specific invariants are that the bids can be placed only when the status of an auction is active. So before starting an auction and after closing an auction, bids cannot be placed. We are specifying that window. When an auction is closed, there is a winner declared, and the winner is the highest bid, is the bid with the highest amount. These are the object invariants of an auction application, and let us see how we use this information to maintain safety. So first, let us look at the updates happening on a single replica. For now, we are not considering the concurrent operations happening elsewhere. To maintain the safety of the local operations, we require preconditions. Consider start auction issued in a state like this, where an auction is already active and there are some bids. This violates our invariant. So we strengthen the precondition of start auction, requiring the status of the auction to be invalid. So the start auction can be issued in an invalid state and changes the state of the auction to active. This ensures a safe execution of a single start auction operation. Similarly, for place bid, to avoid placing bids for an already closed auction, we require that the status be active and no winner declared yet. This enables safely placing a bid without violating any invariant. For closed auction, we need to ensure that there is a winner declared and it is the highest bid. For this operation, the operation should be issued in a state where the auction is active. There are some bids and the highest bid is selected as the winner. So now we have all our operations safe with these added preconditions. Let us see now how concurrency comes into picture. Going back to our state evolution, let us zoom into the European replica where Mark was connected. We can observe that for a single replica, the state evolves either through a local update operation or by merging a remote state containing one or more updates. In this particular case, Mark has issued only a single place bid operation, and he observes Srija starting and closing the auction and Gustavo placing a bid through merge. So he was informed by the remote, by the propagation of the remote states from Srija and Gustavo. So as far as a single replica is concerned, the only point of observable concurrency is during merge. Now let us look into the merge function on a single replica. So we have a local state and an incoming state from a remote replica. In this case, the local state has closed the auction declaring a winner, and the incoming state has a higher bid than the winner. When we merge these two states, the winner is no more the highest bid and the state is unsafe. As we did for the other operations, we strengthen the precondition such that if the status is closed in either of the states, the winner declared should be the highest bid in both states. The prime state represents the incoming remote state. So if we had the same local state with the auction status being closed and a winner declared and an incoming replica state with a lower bid, that would still be safe. Now thinking about a precondition for merge, it seems problematic. We cannot block merging a remote state if the precondition for merge is not satisfied. The state of a local replica should allow a merge at any point of time because merge can happen anytime. Hence, we call it our concurrency invariant. The concurrency invariant should be preserved to ensure safe concurrent operations. It is essentially the weakest precondition for a safe merge, satisfying the object invariant. So now we have our global invariant as a conjunction of the object invariant and the concurrency invariant. We need to make sure that each update maintains this global invariant. This ensures the safety of all concurrent operations. So now we come to a proof rule for verifying safe and highly available distributed objects. If the initial state satisfies both the object invariant and the concurrency invariant, and each operation and merge preserves them, the distributed object is safe in all executions. We use Hoare logic style assertions to verify the safety of each operation and merge. Assume we are executing an operation. We start from a state that respects an object invariant, the concurrency invariant, and the precondition of an operation. We obtain a new state, sigma nu, after applying the new operation. We require sigma nu to uphold both the object invariant and the concurrency invariant. In the case of merge, we require the states sigma and sigma prime, which are being merged, to respect the object invariant and the concurrency invariant. So here, the prime state indicates the remote state which is being merged into the local state. The state sigma nu, which is obtained after merge, should also uphold the same set of invariants. Now let us come back to our auction application and try to apply our proof rule. We have a set of object invariants and concurrency invariants. We already discussed about strengthening the preconditions of the operation to make sure that the object invariants are respected. So now let us look into the concurrency invariant. The concurrency invariant states that the winner is the highest bid in both states. Starting an auction has no impact on this condition since it neither selects a winner nor updates a set of bids. But in the case of a place bid, we observe that a concurrent close auction may violate the concurrency invariant. So if similarly for close auction, a concurrent placing of a higher bid also violates the concurrency invariant. We can observe that scenario in our early state evolution diagram. Here, we see the place bid and close auction happening concurrently, whose results merged into an unsafe state. This can be fixed in two ways. We can either weaken the invariance such that the winner might not always be the highest bid, or we need to coordinate to avoid unsafe concurrency. So now we are focusing on coordination. Let us consider fixing the auction object by using an async wait lock. All replicas require the lock in async mode when starting the auction. As long as the individual replicas have the async mode of lock, they may place bids. When Srija starts the auction, all replicas also acquire the lock in async mode. Mark and Gustavo can place bids as long as they have the async lock with them. So Mark places a €100 bid, propagates his update to Srija and Gustavo. Gustavo places a higher €105 bid. When Srija wants to close auction, she requests the wait mode of the lock. This request triggers the release of async mode locking from all the replicas. When Srija receives the release locks from Mark and Gustavo, the state also contains all their bids. So now aware of all the bids, Srija can safely close the auction, declaring Gustavo as the winner, since his bid has the highest amount. We have implemented this proof rule in a tool called Soteria, which sits on top of Boogie, which is an intermediate verification language. Boogie in turn uses Z3 SMT solver to discharge the verification conditions. Soteria requires a specification of a distributed object. It includes a state represented as the global variables in Boogie, the object invariants given as a function in Boogie with a special annotation at invariant. Soteria also requires a comparison function to determine the relative ordering of states. This is useful in checking convergence properties of the distributed object. We have provided the convergence properties in our paper in detail, so we suggest to refer to that. This comparison function is annotated with a special notation called at GTEQ, which is a short form of greater than or equal to. So that's the ordering relation. The next component Soteria needs is all operations including merge with their pre and post conditions. Merge should be specially annotated with at merge to distinguish it from the other operations. The left-hand side shows the input format for Soteria. We have only shown the skeleton of the specification of an auction. It would also contain the support functions, pre and post conditions, and implementations of all procedures, and of course the function bodies as well. So Soteria checks the So Sartoria takes the specification as the input. It first checks the sanity of the specification. It looks for any syntax errors, and it checks whether the pre-imposed conditions are valid conditions, in fact, with respect to the implementation. And it also uses Boogie to do this checks for it. Then it checks for the convergence properties. So in short, we are looking we are looking for the properties to ensure a semi-lattice so that it is guaranteed to converge. And then Sartoria discharges the proof rule, which we mentioned right now, as safety properties. If all the checks pass, the specification is safe. Otherwise, Sartoria will provide counterexamples to guide the user through fixing the specification. The tool is available on GitHub at the URL shown here. So to conclude, we presented a simple, modular, HoReLogic style proof rule for verifying the safety of highly available distributed objects. We introduced the notion of concurrency invariant that can be derived from the specification, which is basically the precondition of merge. We presented a tool based on this proof rule. The tool uses Boogie, which in turn uses Z3, which is an SMT solver, to discharge verification conditions. As a next step, we are working on synthesizing efficient locking protocols. So we consider the dynamic characteristics of the object as well, like the frequency of the workload on each replica, and also the network characteristics on the underlying network characteristics on which the replicas are distributed. Thank you.